Well, everybody, this is going to be the last YouTube video of the Physics 20 year, actually. We're only going to do one YouTube video during this fourth unit on energy. I'm saving it for this topic here, conservation of energy, for a couple of reasons. Probably the biggest reason why is that this is kind of, I was thinking about this earlier, this is kind of like the greatest hits lesson. We're going to talk about how to take a whole bunch of classic problems that we've already solved in this course. We're going to have a pendulum, we're going to have a spring, we're going to have a pulley system, and we're going to solve all of these questions now. Rather than using kinematics and dynamics, we're going to solve them using energy. Hence my concept of like greatest hits. We're gonna play all the classics again, and we're gonna do them one more time, only just in another way of solving them. So I thought because we have quite a few different examples that we're going to do today. There's actually 5 total that we're going to solve. This is really a really good lesson to probably do as an asynchronous lesson. That way you can pause and rewind and pause if you'd like to, and as you've hopefully been learning as we go along, you can maybe watch this before class, you might watch this after class, you can really do this whenever fits your schedule best. So this will be our second last lesson, and yeah, this is going to be the one that we're going to do that's asynchronous. So let's get started. For some reason, this one thing right here is on top of the word conserve. I'm just going to move that briefly here. Let's see if I can lock that back into place. Okay, so here's our notes. We're going to talk about conservation of energy. And before I begin, I need to point out that this is one of the different physics principles on your data sheet. This is actually the last one we're going to learn this year. We are going to learn 5 in Physics 20 and 5 in Physics 30. And so if you have your data sheet in front of you, or if you just kind of know where I'm referring to, the first principle, number 0, is uniform motion. Number 1 should be accelerated motion. Number 2 should be circular motion. Number 3 we talked about earlier this unit. It's the work energy theorem. I believe this one skips one. I think this one's number 5. This is conservation of energy. And it basically is based on what we learned in our last lesson. We should have done a group lesson talking about different types of system. And basically the concept is that if you ever have a truly isolated system, if you ever have an isolated system in which energy is not lost, then another way of describing that is that energy is conserved. That's the word we use. Conserved meaning that there's only a set amount of energy we have. And so if someone else is going to lose energy, something else needs to gain it. And if we can basically just keep track of energy, we can use that to solve problems. I mean, in another sort of way, like another thing that gets conserved is money. If I were to gain some money, it's because somebody else lost it and gave it to me, right? If I earned $3, it's because somebody else gave it to me. Well, the same thing happens here with energy. If something goes up by 3 joules of energy, it's because something else went down by 3 joules of energy. And as long as you can keep track of how much energy something has, this is another way of solving a problem. And so that's the main goal of this unit, is to be able to solve problems with conservation of energy. And like I said to begin with, that's kind of why I like this as our greatest hits sort of day, because we're going to do a whole bunch of different examples, 5 total. And these 5 different examples are basically going to now be solved with energy rather than with kinematics or dynamics. So let's start with a really basic one. This one is actually more or less a question that was on your first assignment, the very, very first assignment that you had to hand in, right? Assignment number 3. There was an example of how there was a hill, I think, in that one there, and then there was after the hill there was a little bit of a dip, I think, and then there was a ski jump, and then the ski jumper jumps and lands. If you remember this question, so there's a skier at the top of the hill, and the skier is going to go down the hill, and then they were supposed to hit the jump and land somewhere over here, and I asked you to tell me what formulas you would use. And so in theory, you could use a formula involving velocity final, velocity initial, distance, acceleration, and time. That would totally work. But we can actually calculate this question here in a different method. We could use energy instead. And so now one of the things about energy is that we do have to assume we're in an isolated system. And by that, we mean that there's no friction. Because if we're going to lose energy to the form of heat, which we almost always do, but like if we know that we're going to lose energy due to the form of heat, then conservation of energy is not really true. That being said, we've always been assuming that there's no friction, because if there is friction, then there's a force we sometimes don't account for. So, yeah, as long as we're allowed to assume that we have that isolated system where there's no energy being lost, then here's how we might solve this question. Imagine you've got this snowboard on the top of the hill. If he's just beginning, or she, I guess, whoever it is, he or she is just beginning at the top of the hill, we know that at the top of the hill they have no velocity. Velocity initial is 0. But that means that their kinetic energy is also 0 when they begin with. However, they do have potential energy. They have a potential energy of mass times gravity times height. Now, one of the problems is we can't actually calculate that potential energy, because if you look through the question stem, you've been given a height value. That's 23.7 meters tall hill, right? So this is 23.7 meters of height right here. And so we know how tall above the ground the snowboarder or tobogganer, I guess it's a tobogganer, I guess. I didn't even read it. Here I was thinking it was a skier. So the tobogganer is 23.7 meters above the top of the hill. So we know their height, we know their gravity amount, but we don't actually know their mass. But here's why this won't matter when we use energy conservation. When they get down to the bottom of the hill, so this snowboarder slash tobogganer slash skier at the bottom of the hill, at that point they'll have no potential energy because they're now on ground level, but what they will have is kinetic energy. And so the way we can solve this is that kinetic energy is equal to 1/2 mv squared. What's really happening is that as your kinetic energy is increasing, it is coming at the cost of your potential energy decreasing. As one goes up, the other must go down. And as long as there's no loss of energy due to anything, like say friction, as long as we assume that there is no friction causing us to, finger quotes, like lose energy, then what we can do is we can tell you that your 1/2 mv squared at the bottom of the hill will be equal to the mass times gravity times height that you began with. And this is basically how you build your formula, is you build it by putting two energy formulas together, and you say, well, your kinetic energy will become equal to your potential. Or really a better way of phrasing it is that your potential energy became your kinetic. In the same way that work can be turned into energy, well, energy can be turned into energy. Potential energy can become kinetic energy. And that's how you build your formula using the principle of conservation of energy. So if I keep kind of going down here, I'm going to now have 1/2 mv squared. My kinetic energy will come from my gravitational energy. Here's the really cool thing. Mass on both sides cancels. And so I actually don't even need to know the mass of the object. So whichever person it is, their mass doesn't even matter. So two more steps. I need to times both sides by 2 and square root. But if I do that, I should be able to build a formula here for velocity, which will be 2 times g times h, all square rooted. And this really illustrates the whole point of needing to build a formula, is that you don't really want to try to solve for, I didn't mean to do that, let's move that away. You don't really need to solve for the potential energy first, because you can't. You don't even know what the mass is. And since you don't know what this mass here is, or this mass here is, you really can't solve for potential or kinetic energy in either way, and yet you can still use the principle of conservation of energy to solve. So now that we know our built formula, it'll be 2 times 9.81 times by our height, which I'd forgotten, so let me go back up and look. It was 23.7 meters. So 2 times 9.81 times 23.7, and I got to square root the whole thing, and I'll get a final answer of 21.56, which is a meters per second value. Based on SIGDIGs, I guess we got 3. I don't know why I needed to look. I knew it was 3. So the final answer will be 21.6 meters per second. And that's how fast your velocity will be at the bottom of the hill. So again, to solve this question, we took our potential energy and we turned it into kinetic energy. And that's basically how we built ourselves our formula. And again, mass cancels on both sides, and so you can't, like, I don't actually know how much potential energy or kinetic energy this person had, but I can tell you their velocity. And so there's our first example. It can be solved using kinematics and dynamics. If you have enough information, you could say velocity initial was 0. You could say that the distance that was traveled was 23.7 meters. You could say that the acceleration might be due to gravity. Now, technically, this isn't going to fully work because you'd have to know what angle this hill was at. And so maybe more information would need to be given. But as long as there is no friction, in theory, the way that you solve using energy should be the same as with kinematics and dynamics. And I'm actually going to prove that to you on a future question. So for right now, you just have to maybe take my word for it. But you have to try another example now. So here's another one. Like I said, greatest hits. So throwback. We did this kind of question before. We talked about spring constants. Say you got a slingshot. So I'll just kind of draw a bit of a slingshot here. Here's a rim to a slingshot here. Imagine that like you're pulling back on a bit of a cord, and inside of here is some sort of rock or whatever it is you use a slingshot to shoot, and it's going to shoot that slingshot forward, right? And so I'm going to tell you the spring constant was 60 newtons per meter. I'm going to tell you it gets pulled back 85 centimeters, which hopefully you'll recognize immediately needs to be 0.85 meters. it wants to know the maximum height that this rock could reach if you shoot it straight up in the air. So I'm not actually shooting it on an angle, if you can kind of picture this better. I'm going to shoot it just directly up in the air, and at some point when it reaches the very, very peak, it's going to run out of kinetic energy. Because here's your energy transformation. As the rock is in the slingshot, let's see if I can draw the slingshot sideways. As the rock is in the slingshot here, it has energy due to the spring, right? Due to the formula, which is 1/2 kx squared, you have some potential energy in the spring, so I'll call it EP. Your potential energy due to the spring is 1/2 kx squared as this rock is in the slingshot. Then it gets out of the slingshot. Well, at this point now, it has kinetic energy. It has 1/2 mv squared. Until it gets all the way to the very, very top of its arc, and at this point right here, for a brief moment in time, we know that it stops, and so at that point, it has potential energy again due to mass times gravity times height. So if you were to trace the energy transformations, there's really two. What happens is your energy potential due to the spring goes down, which makes your kinetic energy go up. But then eventually your kinetic energy goes down, and the reason why is that your gravitational potential energy goes up. And then really, if we kept transforming this back down, eventually the rock would fall back down to the ground, and what would happen is your gravitational energy due to the rock would go down, and your kinetic energy would come back up again. And really, that's the energy transformations we have. What we have to do is figure out how to build our formula. And so if I was kind of making a flow chart here, I would say that my potential energy due to the spring would be turned into my kinetic energy, which then gets returned back into potential as it's up in the air. So I can kind of eliminate the middleman here and make a formula that says that as long as there's no energy lost along the way, my potential energy due to the spring, which was 1/2 kx squared, it should turn into potential energy gravitationally, which is mgh. And now in this particular example, mass won't cancel, unfortunately. So I will need to know all of my values. So first, let's figure out what I'm solving for. I'm looking for maximum height. So with maximum height, let's scroll that back down. We need to isolate for h, so that means we need to divide both sides by mg. So I can make a formula if I divide by mg. That'll be kx squared over 2mg's. I'm kind of putting the 1/2 of the 2 on the bottom there. There's my formula for height. So let's plug in some numbers. K we said was 60. X we said was 85 centimeters. So that'll be 0.85 squared. In our denominator, we're going to need 2 times our mass, which was 2.5 kilograms. And gravity is 9.81. There we go. We've built ourselves our formula for height. So 60 times by 0.85 squared divided by, and make sure you use like a bracket for the whole denominator, 2 by 2.5 by 9.81. To give you, I made a mistake typing that in. Let me do that again here. 60 times by 0.85 squared divided by 2 by 2.5 by 9.81. Okay. So I have a height of let's see, how many sig digs do I get? Looks like 2. 0.88. And then for height would be in meters, I guess. So 0.88 meters is how far up in the air this slingshot managed to shoot this rock. I mean, it's a pretty heavy rock, actually. It's 2.5 kilograms. That's probably one of the reasons why I didn't make it very high. So, okay, quick recap then. Let's talk about what we accomplished then. We had to build our own formula using law of conservation of energy. So as long as you can keep track of what we're discussing, there was potential energy due to the spring as it's in the slingshot, right? Like as it's in the slingshot, there's potential energy to the spring. As it exits the slingshot, it now has kinetic energy. And as long as no energy was lost, all of that should be transferred. But then eventually that kinetic energy will turn into this potential energy again as it's as high as it's ever going to get to in the air. And we know that the kinetic energy will be completely used up because it's being shot straight up in the air. So for a brief moment in time, it won't have any speed. So think of these as like transfers. I don't know, maybe like use money again. Use money of a bank transfer. You used to have $100 in this account. Now we transferred it to this account, and now we transferred it to this account. And as long as the bank doesn't have any bank fees, stealing money for transactions, which in this analogy is the isolated system where you don't lose any energy. Remember open, closed, and isolated systems? As long as you don't lose any energy along the way, as long as your energy transfers are 100% efficient, then you can use energy to solve problems. Now the problem is that just like with banks, you're going to lose money due to interest and transactions fees. And just like in real life, there is going to be friction, which will cause loss of energy. The problem is, though, when we were doing kinematics and dynamics, we often weren't accounting for friction anyways. So we kind of were allowed to ignore drag. So we're still allowed to. Okay, there's my second example. Like I always say, if you have questions, make sure you stop and ask. That's kind of the point of watching this in class. You can rewatch the video. Otherwise, I'll move on. I've got 3 more examples to track. So here's a throwback question from our pendulums section. Pardon me. So in the pendulum section, we were learning all about how if you have a pendulum that, say, goes straight down like this, but then if you pull it back to this location right here, if I were to draw a free body diagram, and I'm just going to use another color here, hopefully when we're doing this, the force of gravity pulls straight down, but we can break that up into 2 component forces. There's the Fg in the y direction and the Fg in the x direction. And we often called the Fg in the x direction the restoring force because it's what caused the pendulum to undertake its arc. And really this Fg in the y direction is really the doppelganger that helps prevent tension from breaking, because you need this side right here and tension to be equal to each other. Otherwise, if tension's not up to the task, the rope would snap. So hopefully this kind of rings a bell as to how to start this question. But now what we've been asked to do is figure out the maximum speed of the pendulum. Now, the first thing we should consider is, well, where will the maximum speed of the pendulum be? And it'll be right here in the middle. Right? Because when you think of the pendulum swinging back and forth, at its very edge here, your velocity will be 0. And at this very edge right here, its velocity will be 0. But right in the middle, the velocity would be the maximum it'll ever be. So that's what we're really looking to do, is try to find the velocity as it's right in the middle. And the way we can approach that from an energy perspective is that at the very, very edge over here, I'm going to use just another color pen to help illustrate it, but at the very, very edge over here, you're going to have gravitational energy only. You're going to have energy due to gravity at this location here, because it stopped for a second, right? So because of that, there's no motion. But at this section right here, you're going to have kinetic energy only. And the reason for that is that once it's this high above the ground, then, I mean, unless the rope snaps, it can't get any lower than this particular spot right here. So right here, you'd say that your kinetic energy is 0, but you have some gravitational energy, mgh. But at the very, very lowest spot right here, you'd say, well, unless the rope snaps, it can't get any lower. So your gravitational energy is basically nothing, but your kinetic energy is 1/2 mv squared. So if I want to build myself a formula, oops, didn't mean to move that. If you build yourself a formula, you could then say that your kinetic energy is going to come from your gravitational energy, which means that your 1/2 mv squared is going to come at the expense of whatever extra height you had above the ground. Here's the biggest problem then. We have to figure out how much height we have above the ground. We have to know how far it is from here to here so that we know how much height was lost and therefore how much energy was lost. So now let's go through and let's read this question. I've given you questions like this before, not for speed. We have never solved for speed, but we've done lots of questions like this. This particular question here says that if you were to kind of draw a line here, it says that the centimeters was 75 centimeters for string, so that means from here to here is 75 centimeters. And it tells you that it was pulled back 35 centimeters, which, if you recall doing this kind of question in the previous unit, means that if we know 2 of the 3 sides here, we can actually solve for this angle. Right? If you were to use inverse sine, you could solve for this angle. I don't actually care about that angle. I mean, not in this particular question. If you did, you could solve for this angle here and then solve for tension and restoring force, but that's not our goal today. Our goal is really to figure out how much extra height we have above the ground. And the way we're going to solve that is that we know from here to here is 75. And the reason it's 75 is because it's the same pendulum. If it's 75 from here to the angled side, then it's 75 straight down. But if I can find out how far it is in this little triangle right here, if I subtract that from 75, then the rest must be this extra height right here. So to solve for this side right here, which I'm going to label as y, I'll use Pythagoras' theorem. I'll just do it off on the side right here. If I do 75 squared minus 35 squared, square rooted, that should be equal to what side y is here. Because I'm just using Pythagoras' theorem on, I'll use one more color here. There's a crayon, apparently. On this triangle here. Kind of fun drawing in a crayon, actually. Here's this triangle here in black. that triangle right there, I know two of the three sides. I know the 35 side, I know the 75 side, so I'm going to solve for the other side. And let's try that right now. So 75 squared minus 35 squared, all square rooted, gives me an answer for this y value right here of 66.33. Okay, so that means that right here, this is 66.33. Well, that means that although this isn't to scale, this remaining height right here, the one I'm actually looking for, is 75 minus 66. So I'm left with a height value here of 8.6675. And I'm going to save all those values because I may need all of them. So I might actually store that as letter A in my calculator. I'm just going to store that as a letter so that I have that exact value for later. So now, let's go back down to the bottom here. We had said, if you can understand the train of logic here, that the energy we're going to get at the bottom of the loop, the bottom of the pendulum, right, as it's swinging back and forth and back and forth and back and forth, at the bottom of the loop, this thing will have kinetic energy. And it came from at this section right here, it had a little bit of gravitational energy, potential energy. Not a lot, but a little bit. It had 8 centimeters worth. The cool thing is that mass is actually irrelevant. So if I want to solve this question, I don't even need to know how much mass there was. To get V, it's actually the same formula we used earlier today. It'll be 2 times GH all square rooted. So let's try it. 2 times 9.81. And then my centimeters was 8.66 centimeters. So I stored that as letter A, but as I even say it out right now, I recognize that was in centimeters and it needs to be in meters. So although this is 8.66 centimeters, I'm just going to have to take that and divide by 100. So I guess I can do that right in the equation here. I can just take A and divide by 100 to put it in centimeters. So 2 times 9.81 times the letter A, which I've stored, but I still have to divide by 100. And then after that, I have to square root the whole answer. And so I've got a final velocity of, let's call it, how many sig digs do I get? 3, it looks like. With 3 sig digs, I have a velocity of 1.30 meters per second. And so there we go. I've managed to use energy to figure out how the potential energy right here turned itself into the kinetic energy right here, ideally without a loss of energy. We know that's not true. A pendulum will eventually run out of steam, right? Like if you let a pendulum swing back and forth, it might last for a minute, but like over time, it's going to slowly but surely slow itself down. So again, this is only assuming the loss of very minimal friction, ideally no friction whatsoever. Okay, so that's example 3. Again, this was a throwback to the unit that we did with circular motion and oscillators. So if you have any questions, make sure you ask me. If you're watching this at home or sometime later, maybe make a note of it so you can ask again later. Maybe rewatch the video. Hopefully I didn't make any math errors. Otherwise, I'm going to move on to example number 4. So this is another throwback. This is our greatest hit from we did this in the dynamics section where we were talking about free body diagrams. And this is a pulley system where apparently the way it works right now is that we're going to put the 7.50 kilogram box on the floor. And what's going to happen, hopefully you can kind of picture this, is that, well, the 12 kilogram box has more force on it. And so the 12 kilogram box is going to get pulled downwards. And the 7.50 kilogram box is going to get pulled upwards. And I'm going to tell you just how far it falls. It says that the 12 kilogram box is 3 meters above the ground, which means the 12 kilogram box has 3 meters with which to fall. If I were to kind of take stock of our energies before, this is another good way to kind of illustrate it, but our energies before, I could say that really the 12 kilogram box has no energy due to kinetic energy because it's at rest. And the 7.50 kilogram box has no energy because it's also at rest. The 7.50 box has no potential energy because it's on the floor. So really the only energy I have before I began is the potential due to gravity of the 12 kilogram box. That's all I have for energy before. This guy right here has the capacity to fall. Let's consider what we're going to have after the scenario is over. So the instant it hits the ground, what's going to happen is your pulley system will still be here. But what will now happen is your 12 kilogram box will be on the floor, and your 7.5 kilogram box will now be in the air. And I can actually tell you how high in the air the 7.5 kilogram box will be. It'll be 3 meters in the air, right? If this guy goes down 3 meters, this one right here should go up 3 meters. So when we're done, we're going to have potential energy due to the 7.5 meter box in the air. However, we're going to have a few more things. We're also going to have some kinetic energy of the 7.5 meter box because it's going to be on its way up. And we're going to have some kinetic energy of the 12 kilogram box because it's on its way down. Now, one of the things that I may or may not have discussed fully yet, so I want to make sure I'm going to mention it now, is that energy is a scalar value. Energy actually has no direction to it. And so the fact that a box is going up or down really doesn't matter in energy scenarios. So I don't have to worry about adding or subtracting. It's always going to be add. So here's kind of the way I'm going to start building a formula. And this one's a little more complicated than the last one. We're going to have, before we begin, the blue box having the potential to fall down. That's all we've got before we let go. After we let go, blue box is on the ground, so it has no potential energy. But yellow box is in the air, so it does have potential energy. But it's also moving, so it has kinetic energy. And the blue box was also moving as well. The instant before it hit the ground, it was moving as well. So we want to know the speed as it hits the ground. Not the speed after it hit the ground and stopped, but as it hits the ground. So here's how we're going to build our formula. We initially had some potential energy, and it is going to turn into some potential energy, plus some kinetic energy, plus some more kinetic energy. And to help keep things straight, I'm going to make sure that I keep the 12, the 7.5, the 7.5, and the 12. I'm going to try to keep all those boxes straight. So if I want to keep building my formula, it would be this. Mass times gravity times height for the 12 kilogram box will be equal to the mass times gravity times height for the 7.5 kilogram box, plus the kinetic energy of the box on its way up, as well as the kinetic energy of the box on its way down. And that's where we're going to start building our formula. However, this is where a lot of students will maybe make an overly ambitious mistake. Some kids might say, oh, look, there's a mass in every single term. I can cancel it. Unfortunately, that's actually incorrect. One of the reasons why it's incorrect is that the masses are different. Sometimes the mass was 12, sometimes it was 7.5. And so we actually can't cancel mass. We also have one more issue here, a bit of a challenge here, is that we're being asked to solve for the speed of the 12 kilogram box as it hits the ground. Now, if I start to plug in values here, I don't actually want to plug them in. I just want to consider whether I know these values. We know the mass of the 12, the 7.5, the 12, and the 7.5 masses. We know all those masses. We also know gravity. We also know that the height is going to be 3 in both of these examples because the 12 kilogram box was 3 above the ground, and now the 7.5 will be 3 above the ground too. However, we have 2 different velocities right here. And this is more of a math algebra problem, but we need to try to find a way to solve for that velocity. And there's 2 of them. But here's the crazy thing is that the velocities will be the same, right? Won't the velocity that the 12 kilogram box is going down with, won't that velocity be the same velocity as what the 7.5 kilogram box is going up with? So although our equation calls for 2 velocities, they are indeed the same velocity, which means we need to factor. We need to find a way to make it so there's not 2 velocities anymore because they are indeed the same velocity as each other. So if I were to keep going here, we're going to need to do mass times gravity times height. And I'm just going to put a little 12 underneath just to remind us that that's for the 12 box. We still need to make it equal to mass times gravity times height, but this is now for the 7.5 box. And then I'm going to add it to, and now here's where I need to factor. The common term in both of those is the velocity squared. And then what's left over minus the velocity is the 1/2 of the mass, and this is the mass of the 7.5. And then what's left in the other example is 1/2 of mass, but this time the mass is the 12. In order to continue to isolate this for velocity, because we need to know what that speed is there, we have to do a few things. We have to take the mass gravity height of the 12, subtract the mass gravity height of the 7.5, and that's really bringing this term to the other side. We bring it to that side by subtracting. However, we still need to isolate for this velocity here. So then I need to divide by, in brackets, 1/2 of mass for 7.5 plus 1/2 of mass for 12. And if I divide this whole term to the denominator of the other side, I will finally have v squared. For the last step, if I then square root everything, I will now have v. And so I'm going to write this one more time, but this is a pretty intense formula. You may want to watch me do that one more time. But here will be our final answer. It's going to be mass times gravity times height for the 12 kilogram box. We're then going to subtract the mass times gravity times height for the 7.5 kilogram box. And it's really important to subtract them in the right order because the 12 kilogram box will have more energy than the 7.5 kilogram box because it's heavier, which is good because we need this numerator to be a positive number by having big subtracting small. Then comes the factoring portion. And if you are not understanding how I factored this, can you please ask? Because this step right here, where we factored right here and removed this velocity squared along with this velocity squared because the speed is the same, the object that's going up has the same speed as the object coming back down. If you don't understand how I factored that from like a math skill point of view, can you make sure you ask? So, and then I guess one last point here is if you didn't kind of follow that, once you factored out this velocity squared, you're still going to have to square root both sides to get the velocity isolated. So we're now ready to plug some numbers into a fairly complicated formula. So here we go. Mass, 12. Gravity, 9.81. The height that the box was 3 above the ground. We're then going to subtract 7.5 times 9.81 times 3. We're then going to divide this all by 1/2 of, and the order really shouldn't matter here, but I think I first went with 7.5. And then we're going to add 1/2 of 12. And if I square root all of that, I should get myself a velocity. So now we just have to make sure we don't mistype in our calculator. Okay, as long as I didn't make any math errors, I ended up calculating 3.6855, etc. And as I look back at the number of sig digs I'm allowed to use, it looks like 3 meters above the ground was actually 3.0, so I get 2 sig digs. So I'm going to call this 3.7 meters per second. Which means, if you can go back to that drawing there, that as this box was above the ground and this one was on the ground, as they traded places, and now this box hit the ground, and this box is now in the air. It doesn't really matter how fast they're traveling. The one is traveling 3.7 up, which means that the other one is traveling 3.7 on the way down, and that's what we're looking for. The instant it hits the ground, they were traveling 3.7 meters per second. So, kind of an interesting type of question that we can solve, but using energy principles. So, like I said earlier, one of the biggest struggles in this particular question is building yourself a formula. And although much of energy conservation is the same as grade 10, this one right here probably would be a little bit beyond the scope. Maybe you remember doing energy conservation equations before. When I teach my students grade 10 science, I often give them an example of like an object that's in the air and it just falls to the ground. I often do a lab on this actually, where we like drop an object off the roof. And at the top of the roof, it has potential energy, and when it hits the ground, it has kinetic energy. And so hopefully you're somewhat familiar with the idea of building a formula and making kinetic energy equal potential energy, and making, like, say, mgh equal 1/2 mv squared. But sometimes the formula can be pretty complicated, where you actually had quite a few different energies you had to keep track of. You had to know whether it's for the 12 or the 7.5 box. And then this step right here is one of the hardest ones. Isolating for that velocity in more than one location takes a little bit of math skills. So if you are a little lost there, make sure you ask. So, okay, I've got one last example we're going to do. We're going to go back and flash back to one of the first questions we ever solved. It's the type of question where we did a lab on this. We should have done a lab on this, hopefully, where we shot Nerf darts. And basically the Nerf dart goes up in the air, and then it comes back down and it hits the ground, and it has a vector that it begins with, right? And so when it begins that vector, there's an angle in here of 30 degrees, and we find VIY and we find VX, and we solve for this throwing object. And so in theory, we should be able to solve using kinematics dynamics, but we should also be able to use conservation of energy. So what I'm going to do is I'm going to solve the same question twice now and just prove to you that we can actually solve this using the original methods we've learned or using energy methods, and we should get the same answer. And so that's my goal on this last question, then we're done this lesson. So just make some more room on here. So here's your example. The angle is 30 degrees, and it was 16 meters per second that the object was thrown at. And the question says, find me the speed of the rock after it's been in the air for 2.5 seconds. So we want to figure out after 2.5 seconds, what's its speed. And so I'm just going to guess that 2.5 seconds is like, say, right about here. Let's find its speed at that point. So first, let's use kinematics. For kinematics, let's consider what we know. We know that in the y direction, we know velocity initial in y will be 16 sine 30. Hopefully that is something I don't have to elaborate too much on, but this is going to need to involve sine of 30, and Vx is going to need to involve cosine of 30 in order to break it up into its components. So we know VIY. In the y direction, we also know our time value because it says it was in the air for 2.5 seconds. Furthermore, we know the acceleration due to gravity is going to be negative 9.81. That'll be meters per second squared. And so look, we've got ourselves three variables. I should be able to find a velocity final in y. Now, that's only the velocity final in the y component. So I'm just going to find that first, and then I'll come back to what the x direction is. So let's just solve that first. The formula that we would use would be probably this one here. Acceleration is equal to change in velocity over time, which can really be written as velocity final minus velocity initial over time, because change in velocity is subtracting the two. So then if I want to solve for velocity final, I'm going to need to times time up to the other side, and I'm going to have to add a velocity initial. And so in rearranging this formula, this is good practice at the end of the year, because we need to remember how to do all this kinematic stuff again. But there's my formula for velocity final. Acceleration times time plus my velocity initial. So acceleration is going to be 9.81. In the negative, time was 2.5 seconds. And I'm going to add to it, what was that speed? 16 sine 30. And this should tell me then how much velocity final we had. So negative 9.81 times by 2.5. Then I'm going to add to that 16 sine 30. And I got an answer of negative 16.525 meters per second. Now let's talk about that. Why is it negative? Well, because in the y direction, as this thing is on its way back down, it's traveling on its way down, so yeah, it has a negative velocity. But that's not where I'm going to stop, because if I build a vector of this thing on its way down in its trajectory, the downward component is the negative 16.525. But I need to know how much its horizontal x component is. And to solve for that, I'll use x next. In the x direction, we know that the velocity in x is always the same speed. It'll be 16 cos 30. We know the time value was 2.5 seconds. And so if we're looking for the distance, we could solve for distance. But I'm kind of getting a little ahead of myself. I don't really care about time or distance, because what is the speed in the x direction? It's always 16 cos 30. So really this side right here is whatever 16 cos 30 is. So why don't I just try that real quick. 16 cos 30 is actually basically the number 13.85 and such, so on. So if I use Pythagoras' theorem on those two numbers, I should be able to find the hypotenuse velocity, which is really what we're looking for. So I'm going to take 16.525 squared. I'm going to add 16 cos 30 squared. I'm going to square root the whole thing. And I've got a final hypotenuse velocity of 21.5656 meters per second on this hypotenuse. So hopefully you're able to follow that train of thought there. The negative 16.525 came from solving for this value in the y direction, which was down here. The x direction velocity was always 16 cos 30, so unless I've made a calculation error in doing Pythagoras' theorem, I just take this number squared, add them together, square root them, and I've got a velocity here of, what did I say, it was 21.5656. And there we go, I solved it using kinematics. My goal now is, though, to do the exact same thing using energy as well. Because if I do this properly, we should actually be able to calculate energy at that point. So we do need to calculate one more thing, though. In order to use energy, we're going to have to use a little bit of kinematics information. And so I've actually, in my notes, I've actually built a slide that was intentionally left blank, just so that we can now do this again using energy. Let's consider the diagram here. As this thing is up in the air, let's consider the energy transformation. At this point, when it gets launched, all it has is kinetic energy. And at this point over here, when it's in the air, it has some kinetic energy, but it also has some gravitational potential energy, because it's still in the air, right? It'll have less kinetic energy because some of it is still potential in the air. And so if I want to build myself a formula, it'll be 1/2 mv squared when it starts. And then later, it will still have some speed. It'll have less. So this is when it starts. This is when it's ending. Is that a good way of putting it? This is when it's ending. But we've also got some gravitational potential energy. And what we've been asked to do is isolate for the velocity as it's in the air. It's not quite hitting the ground yet, but we want to find that velocity there. So I'm going to first build myself a formula. Now, as part of building the formula, one of the really cool things, though, is that every term has mass in it. And in this example here, the mass is consistent. It's always the mass of the object that was thrown. So, I mean, I don't know that it even told me the mass. It didn't tell me the mass of the rock, but in this particular example, it wasn't necessary, because if you can kind of see that every single term here has mass in it, it means it cancels. So if we're then isolating for this velocity right here, to do that algebraically, you're going to then take 1/2 of velocity squared. You're going to minus gh. That's going to bring this gh over to that side there. The next thing you're going to want to do is take all of that and get rid of this 1/2 here by timesing it all by 2. And then when you're done, you're going to want to square root it all. Now, if you'd like to, you can actually distribute that 2, and you could then say that your velocity will be equal to v squared minus 2gh, because if you can kind of follow how the math is working here, 2 times 1/2 means that the coefficients go away, and you're just going to have v squared. And if you distribute 2 by gh, you'll get negative 2gh, which means that all we need to solve this problem is the initial velocity, which we had, 16. We need to know 2 times gravity times height. And that's where the problem comes in, is at this particular moment in time, I actually don't know how high this thing was above the ground. So we're actually going to have to figure out how high above the ground this object happened to be, right? Because if this kind of makes sense right here. Here is the height above the ground, and I actually never truly found that height. But the good news is that height is really the distance in the y direction, which is really, I mean, we have plenty of variables in the y direction to work with, right? I have a velocity initial in y, I have a time in y, I have an acceleration in y. I just need to solve for a distance in y. So if I go to this slide over here, let's do that. Distance in y, the formula will be velocity initial time plus 1/2 at squared. And I have all those values. Velocity initial was 16 sine 30. We'll multiply that by our time, which was 2.5. And then we're going to add 1/2 of our acceleration, which was negative 9.81. And we're going to multiply that by t squared. So t squared should be 2.5 squared. So there we go. This should hopefully help us calculate our distance in the y direction at that point. So let's try the 16 sine 30 gets times by 2.5. Then we're going to add 0.5 times negative 9.81 times 2.5 squared. And it's actually a really interesting thing in terms of how this question was solved. Apparently our height is actually negative. I want to talk about that for a second. We actually got negative 10.65625. It means that my diagram wasn't actually drawn correctly. After 2.5 seconds, this object that was thrown up, it's actually on its way down, but the diagram hasn't been drawn quite correctly. Probably more appropriate to draw it more like this. It started up here, it went up in the air, and it's actually a little bit lower than it was before. And so it's actually down here at this point. So isn't that kind of interesting how that kind of changes the scope of the question? Is that after 2.5 seconds, yes, it was still on its way down, but apparently I didn't know this at first, but we actually threw this object off a building, perhaps, and as it got thrown up and then back down, it's on its way down. So I've kind of made this mistake on purpose to hopefully try to help illustrate a point. Not that it's a bad thing to make mistakes, but we actually have to change our question a little bit here. It looks like this, at this point right here, is actually the lowest it's ever going to, well, it'll get lower and lower and lower than that still, but maybe I should kind of consider this just like we did in our lab. We're shooting a dart off of a higher object that's eventually going to hit the ground, and I now know that it's going to travel down a net distance of, like, say, negative 10.65 meters. So maybe I need to change how I design my equation. Originally, we're going to have kinetic energy, and we're going to have some gravitational potential energy. And when we're done, when this thing is right about to hit the ground, even though maybe it's not even hitting the ground, but at least when we're done considering it, all it has is kinetic energy. That's actually going to slightly change how I'm going to draw my formula. Because now we're going to say that when we start, we have gravitational energy and kinetic energy. And when we're done, we're only going to have kinetic energy. So when I'd make my formula, it'll be mass times gravity times height, plus 1/2 mv squared. And that'll equal 1/2 mv squared. And what we're looking for is this v right here, the velocity right as it is about to hit, hypothetically, some ground, even though it may still be in the air. Let's just consider that there's ground at that point. So now the cool thing is we can actually still cancel mass everywhere. That hasn't changed. So I'm going to have a formula of g times h plus 1/2 of v. That'll equal 1/2 of v squared. So then to solve this, I should times everything by 2, which means I'll times this by 2, and I'll times this by 2, which makes that go away. And I'll square root everything. And so my formula should be very similar. I'm going to do 2 times gh. I'm going to add the initial velocity, and that will tell me my final velocity. So honestly, as I compare those two equations, they're almost the exact same as each other, just a plus and a minus sign's been changed. So here we go. Let's give it a try. We're almost done. 2 times 9.81 times by the height above the ground, which I've now calculated as 10.65625. And then we're going to add the initial speed, which was 16 meters per second. And when I'm done, it should be my final velocity. So 2 times 9.81 times by that value right there. We're then going to add 16. We're going to square root the whole number. And unfortunately, I seem to have made a mistake because I got a final velocity of 15.00 meters per second, which is kind of embarrassing here because I've just promised that they should be the same value as each other. So I've obviously made a mistake somewhere here. Just going to consider where I might have made a mistake. Let's see, it was 16 sine 30. Yeah, that was my initial velocity in y times 2.5. 1/2 at squared. Should be good there. And then as I go back here and double check, let's see, that was that value right there. That one right there. I may have to just leave that here. I may have to try to figure out where I made my mistake because obviously they didn't work out to be the same. They should have. I never used a distance here, did I? Let's see. Velocity initial in y was 16 sine 30. Yep, sine is the opposite. That makes sense. Time was 2.5. The way I drew this thing right here wasn't necessarily the scale, but velocity final was still on its way down. That makes sense. And that would still be traveling that direction. It would be traveling that one. So, yeah, that makes sense. Okay. I think I made a mistake in the energy section, so I'm just going to double check my calculations in energy. When we began, we started with d equals vit plus 1/2 at squared. Velocity initial goes there, time goes there, acceleration should be negative. Yeah, I'm just kind of walking through things in my mind here. The velocity was on the way up. That's why this is a positive number here. But then on the way back down, acceleration's pulling it down, so that makes sense. Distance should be there. I'm just going to check that calculation again. 16 sine 30 times 2.5. Then we're going to add 1/2 times 9.81 times 2.5 squared. Nope, that distance looks good. So let's see. When I built my formula. We started with kinetic energy, and we assumed it would have kinetic and potential when we're done, but we were incorrect on that. It's more like this. It's going to go up in the air and come back down like that, which would mean, that we started with a height of 10.65. Timesing that by gravity and height, adding more velocity up. Yeah, the initial velocity was 16. I don't see my error. I'm just going to try my calculations one more time. 2 times 9.81 times by 10.65621. We're going to add 16. We're going to square it. No, I got 15 again. Okay. You know what? I mean, because this video is hitting 50 minutes here, maybe I'll edit it if I can find my mistake, or you know what, maybe I'll leave the mistake for right now, and I'll double check with any of you guys, see whether or not you can find where I made an error. But that's how you'd solve a conservation of energy question. I must have a typo somewhere that I'm missing somewhere along the way. So why don't we call the video there? I'll try to look for the mistake and try to see why it's not working, and maybe you'll find where I made a mistake. In theory, I should be able to have done that with this example here. Oh, I know where it is. I see it now. Oh, sheesh, Chris. Ha ha ha. You know what? I mean, I make mistakes just like you guys do too. That's why I didn't want to give up on this just yet. I finally see where it is. I had to look back at this work right here. Look at this. See how in the previous example of work, I had velocity squared right here, which was 16 squared sitting right here. But that was in the wrong order because I didn't need a minus sign. I needed a plus sign. And now when I go back and look at this work right here, I realize I made a mistake. It's the silliest mistake. How many times have you guys made a mistake on a test? Oh my goodness, look at this. I did 1/2 of mv. I didn't do 1/2 of mv squared, which means this should be squared, and this should be squared, which means that 16 should be squared. So you know what? If any of you managed to catch that, kudos to you. You know, and hopefully this will illustrate to you that, look, even I make silly little mistakes. It's fine. It happens. You're human. It's physics, right? Like you're allowed to make little mistakes. So I'm going to try this one more time now. I'm going to add 16 squared before I square root it. Ah, there we go. Okay. That one little change solves all my problems. I'm not so embarrassed anymore. And you know what? For the last YouTube video of the year, I still got 21.56 meters per second. Which, by the way, when I do it properly and I actually put a squared sign right here, if I go back and double check, it was 21.5656 the other way there too. So sorry that I kind of wasted 3 or 4 minutes here just kind of fumbling around trying to find my mistake, but you know what? That's life. That's how things go. That wasn't intentional, by the way. That's just kind of how things break. So I'm not going to edit that out, actually. I think I'm going to leave it. I'm going to leave my mistake, and hopefully you'll kind of understand the process that I went through when I recognized, ooh, something's wrong. Better go back and double check, right? And look through every step along the way. So, okay, we're at 52 minutes. Let's wrap things up. So here's what we've learned today. You need to be able to build yourself a formula where one form of energy is probably equal to another form of energy, but I don't know exactly what the formula looked like. It could be mgh equaling 1/2 kx squared. It could be mgh plus 1/2 mv squared equaling 1/2 mv squared. It really depends on the context. And so you've got to really draw yourself a good diagram and consider what sort of energies are in play. But there's really only 3. There's this one here for potential energy, this one here for kinetic energy, and this one here for the elastic potential energy. Some of those in combination will make up your formula, and so you've got to have really good skills at being able to build formulas. The good news is that we've been building on this all year long, and you may even have had some practice on this in your grade 10 course, because there are some questions that hopefully you answered where, like I said, a lab that I often do is I have someone drop something off the building. And what ends up happening is their gravitational energy turns into kinetic energy. And so once you get the hang of how that works, then you can start building your formulas. So, okay, last thought that I'm done. I do have a worksheet that you should do for practice. It's not for marks, but you should do it. It's worthwhile. It'll be good practice for you to get used to things. So, and that's it. We have one last lesson left. It's going to be on power. We'll probably do it in the next couple of days. It's not overly long. And that'll be it. That'll be it for our course. So, okay. Thanks everybody for watching the video. Hopefully this was helpful, useful. Hopefully you got a chance to pause and rewind or watch at your own pace. You definitely got a chance to watch me make a mistake and kind of solve my way through it. And you know what? Even that is probably valuable. So, okay. Thanks everybody. We will talk soon.